We've been reviewing standard tricks that apply to integrals defined in terms of trigonometric functions. So in this review of standard techniques, now we're going to take a look at functions that are defined in terms of secant, cosecant, tangent, and cotangent. Just looking at a few examples. To start with, let's take a look at the antiderivatives of secant and cosecant. I'm just going to give you the formulas and we're going to verify at least one of them. An antiderivative of secant is given by the natural log of absolute value of secant x plus tangent x. That's up to a constant. Similarly, an antiderivative of cosecant x is given by negative natural log of absolute value of cosecant x plus cotangent x, up to a constant. To verify such a formula, all you have to do is differentiate the function on the right hand side and verify that you obtain the function that is under the integral. So let's verify the first formula by differentiating natural log of absolute value of secant x plus tangent x. We've already verified when we were looking at the natural log that the derivative of natural log of absolute value of x is 1 over x. So just using the chain rule, here we have natural log of absolute value of some function. We're going to get 1 over the function under the absolute value multiplied by the derivative of that function. In other words, we get 1 over secant x plus tangent x, and then on top we have the derivative of secant x plus tangent x. The derivative of secant x is, well, derivative of 1 over cosine. You get the derivative, the opposite of the derivative of cosine, in other words sine x, divided by the square of cosine, and therefore this can be expressed as sine x secant square x. On the other hand, secant square x is the derivative of tangent x. Now what can we do with that? You see that at the top we have a secant square that we could factor out, and we would have therefore secant square x multiplied by sine x plus 1. What about the bottom? Here we have this tangent x. Tangent x is really just sine x over cosine x, or in other words, sine x multiplied by secant x. That means at the bottom we can also factor secant x, and the second factor is 1 plus sine x. So this is what we get. Secant squared times 1 plus sine x divided by secant x times 1 plus sine x. Of course, the common factor 1 plus sine x cancels out. We end up with secant square over secant. Cancelling out one of the secant x, we obtain just secant x. And that verifies the first formula. Of course, the calculation would be pretty much the same for the second formula. Now what can we do with that? Let's look at something a little bit more complicated. Let's say we're looking for the integral of secant cube x. Well, the first thing we should look at is there any kind of substitution we can use? And the derivative of secant is sine x secant square x, so we might be tempted to try to go for that and write secant cube as secant times secant square. However, we don't really get the derivative of secant. We get the secant square, which is just part of what we need, right? We would need a sine x in order to get the derivative of secant x to appear. So here, it doesn't seem very helpful to use substitution. What else do we have in store? Well, we can try to use integration by parts. Secant cube is really a product of secant x by secant square x. And then we can maybe try to do integration by parts on that. Secant x, we just have established a formula to obtain an antiderivative, but it's not a very nice one. It looks complicated to integrate this. We know how to differentiate it though. The derivative of secant x is just sine x secant square x. Secant square x on the other side is easy to integrate because it's a derivative of tangent. In other words, an antiderivative of secant square is tangent x. So we can try to use integration by parts, differentiating secant x, integrating secant square x, and we obtain for du sine x secant square x dx, and for v tangent x. Using the integration by parts formula, we obtain uv, in other words, secant x times tangent x, minus the integral of v du, in other words, minus the integral of tangent x sine x secant square x dx. Well, that second integral doesn't quite look like something much simpler than what we started with. However, we can simplify that. This tangent x here is really just sine x over cosine x, in other words, sine x times secant x. So I can write it that way, and then multiplying things through, we get sine square x secant cube x. And now we can observe that sine square x is really just 1 minus cosine square. This 1 minus cosine square is good for us because secant cube x is really 1 over cosine cube. So if I write this way, what I obtain multiplying things through is the integral of secant cube, and then I have cosine square times secant cube, and that's just cosine square over cosine cube, in other words 1 over cosine, that is just secant. Because of this cosine square is really 1 over secant squared. So here is what we obtain. Secant x tangent x minus the integral of secant cube x dx plus the integral of secant x dx. For the last term, we have a formula at the bottom. And well, now it looks like we didn't gain anything because we started with the integral of secant cube and we have the same integral to calculate. But that's not quite right, precisely because we have the same integral, this integral that we are looking for appears here as well, but with a different sign, so we can solve for this integral. Namely, I can add integral of secant cube x dx on both sides, and I obtain 2 times the integral I'm looking for is equal to something I can calculate. In fact, this integral, that is the part missing, is given by the formula at the bottom. So now the integral of secant cube x dx is 1/2 of the sum of secant x tangent x plus an antiderivative of secant x, which is given by natural log of secant x plus tangent x. All this is, of course, up to a constant. Now let's look at another example that involves power of tangent. Integral of tangent x to the 4th. Again, we might try to use some sort of substitution, and we have a power of tangent, so the natural thing would be to try to use substitution with u is tangent x, but then we need to have the derivative appear. So remember that the derivative of tangent x is secant squared, which we can also write 1 plus tangent square x. Okay, let's see if we can use that to rewrite this under a form that we can use. So tangent to the 4th is really tangent square times tangent square, and we can write one of these tangent square as secant square x minus 1. Multiplying things through and splitting the integrals, we obtain the integral of tangent square times secant squared minus the integral of tangent squared. In the first one, we're in good shape because now I have integral of tangent square x multiplied by the derivative of tangent. So this integral I'm going to be able to deal with by substitution using u equal tangent x. On the other end, for this other integral, we have integral of tangent square. Well, we can use again this observation that tangent square is the same as secant square minus 1. And then we have integral of secant square minus 1. Integral of secant square, I know how to get that. Integral of 1, of course, I know how to get that. So we rewrite tangent square as secant square minus 1, and we obtain this first integral that we know we can deal with by substitution, minus the integral of secant squared, plus the integral of 1. Secant squared is the derivative of tangent, so an antiderivative is just tangent. So I obtain this integral of tangent square secant squared, minus tangent x, antiderivative of secant squared, plus x, antiderivative of 1, plus a constant. And then, for this first integral, we've seen that we can use substitution because this secant square x dx is really du if u is tangent x. So we do this substitution, u is tangent x, du is secant square dx, and we obtain the integral of u squared du. And of course, this is just the antiderivative of the power of the variable. We get u cubed over 3, where u is tangent x. In other words, we get tangent cube x over 3 minus tangent x plus x up to a constant. Now it's time for you to turn to some homework.